some of these things, they've got the probably. They're gonna be EDS. And they're EDS, we won't make a conflict with the. The security that we're trying to get. Yeah, they want to buy it, you know. It can't be tolerated.
Yeah, I agree.
There's something. But I think for here. Right, you want to see it. And I've lost it. Maybe you're aware. Now,
Yeah.
Okay, thank you everyone for coming. Let's go ahead and get started. Sorry for not hearing me well. I have to wear a mask because my kids have a cold, and so now it's my turn just to be naughty and have a headache. So don't ask me any questions. I'm very happy to welcome Dr. Dennis Kim to our this week's research seminar. He did his bachelor in chemistry from the University of Massachusetts Amherst in 2011. And he obtained his PhD in material science in 2018 from Caltech. I was at UCLA with Prineha Narang and at MIT with Jim LeBeau. That already tells you he's an expert in state-of-the-art electron transmission electron microscopy. Currently, since the fall of 22, he is a research scientist at UCLA, so he crossed the country a few times. His research interest is tomography, and I'm sure you will see some of that here. And he's interested in thermal quantum and energy sciences for the field of research. And with that, I thank you for coming, and I'm looking forward to your talk.
All right, thank you. Let me see this one. Can everyone hear me in the back? All right, good. Thank you for the very kind introduction. I guess I'll just kind of jump right into it. Maybe. Okay, there we go. So generally, I think the theme of my goal actually in the future is to be able to really start to engineer materials by design. And what do I mean by that is essentially is, you know, can we actually utilize computational methods, and can we actually pressure and volume? But effectively, you know, can we use these computational methods? Can we actually account for all of the degrees of freedom within our materials to try to build up different technologies, whether it's for structural applications in transportation, energy, or even different new microelectronics, right? So effectively, can we get to the point where all we have is structural information and the elemental specificity, and can we actually kind of solve materials problems in this pipeline? What I mean is you can think about two competing phases as you see your alpha, your FCC, and your beta phase, BCC, and you know that there are electrons in your system. If it's magnetic, you also know that there can be spins or magnons. And of course, at any finite temperatures, you're going to have your lattice dynamics or your phonons. Right. So can we actually build up all of the entropic components from the microscopic viewpoint of, do we know what the electrons are doing? Do we know how they're interacting? Maybe they're interacting with your phonons, or even, do the phonons as quasiparticles interact with themselves, and how do those ramifications actually show up in our free energy, right? So this is kind of a mock-up of some of the contributing factors that you might have seen in your coursework, where you can have your configurational entropy, your electronic, your vibrational, your magnetic, and then some general term where you can do that similarly in the vibrational components as you're counting the phonons and the energy distribution. You can either do this in a couple of ways. One is you can look up the NIST-JANF tables, where there has a large database of different heat capacities, but you can actually also do this at your Oak Ridge National Laboratory with using inelastic neutron scattering techniques, right? So you can get experimentally phonon dispersions with very high accuracy and precision, and you can actually compare them with our heat capacity measurements, right? And we can see that, as we track our experimental data with temperature, we should see that it matches up very well with our heat capacity measurements. But not only that is we can actually compute our entropies simulated, right, in the computer. So this is a simple case where in a bulk system like silicon, you can actually start from your structure. You can actually calculate all the components of your free energy and compare them directly to your heat capacity measurements, or kind of use this information to drive understanding phase transformations or transitions. But what happens if we actually don't know the atomic structure information, right? In real crystals, it's actually quite rare to find perfect single crystals, right? Boundaries, chemical ordering, defects, surface structures, or especially the amorphous phase, right? Once we start looking at more disordered systems, there is a little bit of a need for advanced characterization tools, right? So we need advanced characterization tools, but not only that, as we move into the future, we have to be able to see these materials in 3 dimensions. So when you first think about trying to understand the atomic configurations and your structure in your materials, you can probably think about Bragg diffraction experiments, where Bragg was contributed the Nobel Prize with his father in 1915, where you can get a lot of analytical and quantifiable information from this. The only issue is that normally you have a decent sized system. You're not truly at the atomic scale, meaning that although if you assume periodicity, you have that information, that a lot of times you don't know exactly where the defects are. The next thing that you might think about is imaging these systems in real space, where you can do in the electron microscope, where now we have truly high spatial resolutions, where you can see small dopants in their silicon film, but we're still actually seeing the projection, right? So we're looking down atomic columns. So we might know that there might be 1 defect or 2 defects within the column, but we don't know exactly where they are or where they relate to one another. Electron microscope, and we can actually rotate our sample compared to relative to our detector, and using a Fourier slice theorem, where we know that a projection in real space is equivalent to the Fourier space projection, that we can actually iterate back and forth between real and reciprocal space, and what you end up finally is with a 3D voxel volume, right? So we can apply specific constraints, and I'm going to kind of skip over some of the details here. But finally, what we have is this 4-dimensional object, right, or 3D voxel intensity. And I'll kind of hope to show you what that's like and what the type of data that we use in our experiments. On the left-hand side is an atomic scale rendition of an iron platinum nanoparticle. And on the right-hand side is the actual voxel intensity data. And when I start this movie, we're going to actually be slicing through this 3-dimensional data. And what you'll see is it's in a jet color scale. so that the brighter or the hotter spots will be actually our platinum atoms, and the lower green kind of bluish area would be our iron atoms. So you can start to see this is a crystalline material, and as we're going through, we can start to see now we can actually pinpoint all of these spots and have true 3D atomic coordinates. Is you go to the TM microscope, you spend a lot of time finding the system of interest, and you actually rotate your holder and you get around 60 or 70 or so images. And you can actually build them up and kind of go through this workflow that I'll just show you. Just one of the things to note is we do a lot of work in algorithmic design of trying to account for drift and scan distortion, whether it's denoising or background subtraction, so we can get high fidelity data. Just to show you an example, I won't be really talking about this today, but what we've done before is trying to look at actually the atomic scale chemical ordering in these iron platinum magnetic materials, right? So one of the things you can do is you can put your sample into the microscope, do this tomographic reconstruction, take the sample out, heat it up in ex situ, put it back in, and try to really start to see what the atomic scale ordering happens in ex situ. But today I'm going to be focusing on two separate projects that we published recently. One is on the actual atomic ordering of amorphous materials that we've shown for the first time here. This is an atomic rendition that you might notice from my title slide, where these atoms are actually tantalum glass film deposited directly onto our TM. I'm focused on the amorphous side. So what is a glass, right? Glasses are actually ubiquitous in nature. A lot of you have maybe seen it in the glass that you drink out of, or even phosphate glasses and through optical cables. Normally, we think about them as having no periodic structure, right? Something that's kind of trapped in the liquid state. Whereas you can kind of see this blown glass here would have a disordered atomic coordinates compared to the quartz crystal on the bottom. And when you might think about glasses, you might be thinking, okay, from the atomic perspective, right? We understand that a lot of times these glasses are ceramics, but what about the electrons? Meaning, can we have a metallic glass? And does that offer kind of unique opportunities from an engineering standpoint? There's been a lot of work in metallic glasses, and I'll show in the next couple of slides, but they do have some very interesting applications. Right here on the right-hand side, it's a log plot between yield strength on the x-axis and toughness on the y-axis. And one of the reasons why there was a lot of interest in metallic glasses, as you can see on the top right-hand side, is that these systems are not only strong, but they're actually tough, right? There are other benefits of having metallic glasses, as like you would see in the more polymer science applications, that you can actually injection mold deformation mechanisms kind of cause you to create these shear bands, and you have catastrophic failure, right? You don't want to be in an airplane and have it kind of catastrophically fail in the air. You can think about it that way. So how do we get a glass? David Turnbull, back in 1949, when he was at General Electric, before moving to Harvard, he theorized that if you could cool something fast enough, that you'll always get a glass. Meaning, if you look about, you can think about volume and temperature on this graph here, as you're in the liquid state, if you're cooled sufficiently fast enough, you can kind of bypass crystallization and kind of get trapped into this amorphous phase, right? So you can even think about it on your potential energy landscape, where we know based on thermodynamics, our crystalline phase is the lowest energy, but you're kind of bypassing this and getting trapped in one of these metastable states. Paul Douay, actually at Caltech in the 1960s, was able to first synthesize metallic glasses in a gold silicon alloy, where he did a quench splats kind of synthesis, where he would catch a floating nanoparticle of gold and silicon between two copper plates. And he was actually being able to show that for the first time. Now, those cooling rates were about 10 to the 7 Kelvin per second. So it's quite fast. And there's been a lot out that you only have to cool this alloy at 1 Kelvin per second to actually trap it into the amorphous phase. And another way you can think about it, as you've probably seen in your coursework, is the time temperature transformation diagrams, where effectively, kind of similar to the graphic on the right-hand side, is that instead of kind of cooling sufficiently slow enough to form your crystal, you're actually bypassing it and staying kind of in this amorphous phase, right? There's a lot of work and a lot of engineering that goes into this, but one of the things that I was always most interested at is, what are the actual atomic structures of these classes, right? Do we actually know how the atoms kind of correlate in 3 dimensions? What are not only the short range ordering, but actually the medium and long range order as well. In 1950s, F.C. Frank performed kind of one of the seminal ideas for metallic classes, or amorphous systems, where he took 13 atoms, as you can kind of see here, and he found, using Monte Carlo, what's the actual lowest energy state. So he hypothesized that he calculated that that 13 atoms in isolation have lower energy as an icosahedron than in the FCC or HCP phase, right? And that's nice if you have these kind of atomic clusters and 13 atoms. So there are 12 of them that are kind of surrounding our central atom as you rotate around. There have been many attempts to actually try to study these atomic configurations in glasses, whether it's through kind of your calorimetry data. You can take TM micrographs, so you can start to see that, yes, we have some disorder, but we also see a small few clusters that kind of point back to this 5-fold symmetry. There has been nanobeam electron diffraction, where it's very simulation heavy, considering that you're only looking at specific spots. So although you can kind of start to correlate between your nanobeam diffraction data and small clusters, you don't actually get the full 3-dimensional space, right? Or it's not space filling. There's always diffraction experiments where it relies on reverse Monte Carlo. So it always relies heavily on molecular dynamics simulations, right? And it kind of, to trust these experiments, you must trust your potentials, right? So it's very limited based on how good your actually atomic potentials are. So the natural question was, we say that we don't assume anything about crystallinity in our atomic electron tomography. So to test the limits, we looked at these 2 glass systems. These are 2 non-vitrified systems. They are in the nanoscale. So one is and we go through the same procedure that I kind of outlined, and we'll see that we get the atomic structures on the left-hand side, right? So one of the first things that we wanted to see was, do we know that these systems are actually amorphous? And from our FFTs, we do see that that's true. But not only that, it's because we have the actual atomic scale information, we can actually calculate the bond lengths and how they orient themselves in real space. Right, so this is a bond order orientational parameter, but effectively we're templating, right? So we're projecting each bond onto spherical harmonics and comparing them to what those values would be for the crystalline phase. I don't know if it's hard to see in the back, but we do see that the crystalline phases are on the top of this kind of y-axis, and all of our experimental data is kind of on the lower left. Just to kind of make sure that we're not overcounting our amorphous phase, we've kind of drawn this cutoff or magnitude, and I've separated the crystalline features that we see on the surface here and in the tantalum glass here in gray atoms, where the more amorphous phases in the colored, spheres. So typically when I look at, like we saw in the iron platinum data, it's quite easy to orient the crystal because we know that we see atomic clock. Features, or there's no crystallinity, but if you can kind of notice here on the top and kind of on the surface here, is we're starting to see some ordering, the nucleation that happens on the surface, and that's not unexpected. And I'm kind of rotating the system here, and I will uplift the crystalline atoms, and you'll see that at least within the crystal, or within the inside of the crystal, that we see it is fully amorphous. This can be shown in the same way in the palladium nanoparticles, where we kind of see our crystallization that happens on the surface. But as I kind of expand and explode this nanoparticle, we can see at least internally that it is fully amorphous, right? And that's something that's important, as you would expect that we wouldn't have homogeneous nucleation versus a heterogeneous would be more common. The second thing to do is typically, as you'll kind of see in molecular dynamics simulation papers, is they'll perform an analysis called Voronoi analysis. And what that basically does is that polytetrahedrally kind of breaks down your nearest neighbor bonds and sees what the actual symmetry takes place on the outside, right? So in this case, you can see that you can either have 3, 4, 5, or 6-fold symmetries for your short range order. And what we can do is actually now compare our experimental results where you have these 13 atoms that have all 5-fold symmetry clusters. But what we see in our experimental data is that's not the case, right? We know that there are 45% of our short range ordering has 5-fold symmetry. They're just not aggregated into these perfect icosahedrons. So then the next thing that we wanted to ask was, okay, that's for the short range order. Can we answer actually anything about more of the medium range order? So we ended up doing this polytetrahedral packing. It's very similar to Voronoi analysis, but a little bit different, where we kind of pick up all of, we have a metric to determine if you have a good tetrahedron. And if they're phase sharing, if they're phase sharing, then we say that they're bonded. Meaning that if we had a perfect icosahedron that you can kind of see on the right-hand side, that it would have the skeleton or this dodecahedron of 12 pentagons, right? So one thing just to note, a little bit hard to see, is we're going to be comparing the 4-fold symmetries, 5-fold symmetries, and 6-fold symmetries. And if we did have the actual icosahedron motifs, then we would kind of see these 5-fold symmetric soccer balls that you see on the bottom right. And the interesting thing about kind of analyzing our 3-dimensional data this way compared to the Voronoi analysis, and we do see that we have majority of our polytetrahedrous do have 5-fold symmetries, as we would expect. But some of the things that we can actually do is try to look at the atomic density, right, at the atomic scales experimentally, right? So we can start to correlate the atomic density with our networking. And as you had mentioned, if you have closer or localized bonding in our polytetrahedral network, that it would correlate heavily with our mass density. Now, this doesn't yet answer questions about what the medium range order is like, right? So I've talked a lot about, yes, it was predicted that we were supposed to see icosahedrons. We don't really see that. And now we see that, you know, some of these icosahedrons are not really filled, right? So that instead of having maybe 12 pentagonal bipyramids, we're only seeing 1, 2, or 3, right? So if you kind of look at, if you assume that each atom center has a specific icosahedron site, we can see that there are really there's maybe one, I believe, if I remember correctly, or no icosahedron at all in our systems, but all of our icosahedron sites maybe have 1, 2, or 3 5-fold symmetries, right? And this is quite interesting because, you know, not only just one space filling, right? So this is around a couple of nanometers from head to toe distance. And you can see that this largest pentagonal bipyramid or network of 5-fold symmetric short range ordering kind of shown here on the right-hand side, where the lower part is just the skeleton of our polytetrahedral analysis. These are just a couple of examples that we see. So, you know, sometimes we do see kind of shorter networks compared to longer ones in the nanofilm, whereas in the nanoparticle, all of our pentagonal bipyramidal networks kind of end up being around the nanometer range. So, you know, that kind of begs the question, was our experiments incorrect? Were we doing something maybe wrong, or, you know, is something wrong with previous simulations? And I think it's kind of in the middle, meaning that we did perform our own molecular dynamic simulations. And what we did find was that, yes, you can actually have pentagonal bipyramids that are very highly dense, which correlates really highly to having a system with high numbers of icosahedron. But in our experimental data, it actually looked more closely like high temperature melt, right? Which is kind of begs the question, well, is our that landscape, right? It's actually basically comparing the glass state in this blue circle versus this green circle. Because we're non-vitrified, we didn't actually do any pre-processing, so we didn't heat treat it or do sonication, right? So we're actually kind of trapped in this higher energy stage, which is probably why we're seeing such a low concentration of icosahedron. Right, and this concept is not necessarily new, especially in the molecular glasses. You can toy around with kind of holding your substrate at different temperatures, and you can kind of play around and see that you can get rejuvenated, high energy, or relax in your low energy state. Now, I think in general, this kind of creates a lot more questions than answers, but this was kind of the first instances where we were actually able to experimentally see these atomic configurations at the atomic scale in 3D with 3D precision. I'm going to switch over a little bit to more of the 2D materials, but if you have any questions, please don't hesitate to interrupt me. Okay, so the second kind of part of my talk, I'm going to be talking about the atomic scale correlations and the strain that we can see in 2D materials. 2D materials are really interesting, and I think I'm a really induce atomic scale defects. You can change the rippling, right, or your substrate effects. You can look at line defects, or even nowadays with your twisted systems, you can create these Mori patterns, right? And one of the kind of basic questions that I was wondering is if we want to introduce 2D materials more into the mainstreams and have them show up technologically, you have to kind of, especially if it's going to replace our semiconductor industry, you should be able to freely dope them and play with kind of your N and P type doping systems, right? So one of the things we were wondering is if we have a system of moly disulfide and we were to dope these with rhenium atoms that would technically bring in one extra electron, would this be just like in the silicon case where you would have some nicely defined defect states and the rise in your Fermi energy? Right. One thing to note is that there was some work previously showing that not only can you dope rhenium disulfide or rhenium atoms into moly disulfide, you can actually start to go from your doping to alloying and then to kind of have this structural phase transformation. So in the same sense that I showed in the iron platinum particle and in the metallic glasses, we can actually do this analysis on our two-dimensional films. Tomography is not only can you see that there are sulfur vacancies, but you can actually start to see what side of the film they're on. So in this case, sorry for the contrast, I guess you'll have to trust me on this, but you can see here that there is a vacancy on the bottom, and then that there are vacancies kind of on the top and bottom and on the top here, right? So normally when you think about transition electron microscopy, you can now detect where the defects are, but you really have to go to 3 dimensions to be able to see where they are if they're on the top or the bottom of the film. So we can do the same type of analysis that once we have the actual atomic coordinates, we can start to look at the actual atomic bonding, right? So one of the things on the left-hand side, this is the z-axis. So you can see that there is quite a bit of rippling in this film, right? And we're able to capture that. But not only that is we can start to separate the bond difference between our molybdenum atoms and our sulfur atoms, right? And we can see that although the whole film is the same system, it's a rhenium dope, around 3% rhenium doped molybdenum disulfide, we can actually see that there is a strong localized correlation between atomic scale defects. So if you can see the histogram on the right-hand side, it's a bond length as the x-axis, and the for vacancy, right? As you can kind of see here on the right-hand side. Now, this is another movie that I made, and this one is I'm going to be transitioning back and forth between what a pristine model would be and what we see in experiments. So when we're on the pristine model, it's going to be a little bit lifeless or have less color. And when I transition back to our experimental coordinates, it's going to have a little bit more color, and then I will actually light up the atoms in red, right? The rhenium atoms in red. So you can see here that we see this cluster of rhenium dopants, and you can really start to see a lot of strain, atomic scale strain happening. Kind of in this planar view, you can also see that the type of out of plane strain from our sulfur atoms that you would see, right? And this is kind of happens throughout the film, and it's very localized near our rhenium atoms. And that was actually seen for the first time, I guess, in a two-dimensional material. So if you just kind of see on the right-hand side, or even here on the left-hand side, where as we're kind of looking at the atoms around our rhenium dopants, we do see a lot of atomic scale distortion. So because we have this picometer accuracy, we can actually start to look at what you'll see is that close to our rhenium atoms, we see the most amount of strain, not only in the X and the Y directions, but also in the Z plane. And this is really the unique part about our atomic electron tomography, is we get true three-dimensional atomic level strains that you normally wouldn't get. And that is all nice, but can we take this actually a little bit farther? Are we just showing the atomic level strain, or actually, can we actually use this information to kind of look at our actual materials properties? Oh, I skipped the slide. Okay, so like I mentioned before on the previous slide, we do see a lot of rhenium dopants and strain around the atoms, and these are just the histograms to show you that that we can quantify that, right? So if we isolate the areas within these kind of red circles, which are all surrounding rhenium atoms, we do see that that correlates to the black histogram on the bottom, where our purple or bluish histogram is just everywhere else, right? So even though this is the same system, you can actually start to isolate what area you're looking at. And these atomic level strains are actually a lot more localized than I would have expected, at least. Okay, back to my band structure method was pioneered by Alex Zunger at the University of Colorado. But what you can actually do is actually use a larger or a supercell, and you can actually unfold your band structures into the unit cell. And what this allows you to do is actually make something that's a little bit more palpable and something that we're used to. So in the perfect sense, you have this unit cell, you would have a specific band structure. And you know that your reciprocal space is inversely proportional to your real space distance, so that if you have a supercell or larger supercell in real space, then you would have a smaller cell in reciprocal space, right? So then you unfold these band structures and you can get exactly back to your unit cell case. In the same way that if you introduce any distortions or alloying, you can actually capture that information back so that we can actually compare our unit cell to our real system using different areas of our experimental coordinates, right? And then I'll kind of just show you an example here where we found an area that's just pure moly disulfide with no defects in the same system. And we can see that in regular 0 Kelvin ab initio methods that you would get exactly what you would expect, right? A nice semiconductor with a band gap. Where and you can actually see that here. So that we have, due to the fact that we have experimental strain, you're seeing a lot of shadow bands and a distortion of our electronic band structures, and even the changing from a direct to indirect band gap that you wouldn't really expect. Now, if we choose areas with rhenium dopants, we get something even more interesting, right? So if you imagine, like I mentioned before, if you introduced a defect, you would kind of expect nice defect states within the band gap, as you would get if you just calculate this with pure computational methods. But the fact that we have our experimental coordinates, you can see that it becomes a lot messier, right? We have a lot of filling of the gap and a lot of defect states that kind of populate within the gap. And we can do this for many regions of our sample and actually compare them. So this is a graphic of density of states, so that you would see that you're in the blue curve, we see a pure moly disulfide area with a nice pristine band gap. Whereas in the red curve is to show theoretically what we would get in those same areas if we were to have a relaxed structure, right? A 0 Kelvin pristine structure, meaning that we still get a decent band gap and we have a few defect states. But what we see in our experimental materials is that we have more of this metallization or the film case, we see the pristine moly disulfide band gap as you would expect. On the middle row, we see the relaxed 0 Kelvin theoretical structures where you would see nice states. But in our experimental data, we see kind of this filling of the gap, right? So that not only are we introducing defect states because of our extra electrons essentially, but because of the local atomic level strains, we're actually closing this gap altogether. We performed photoluminescence spectroscopy to try to see if this matched with reality. And we saw that it basically did, right? So in moly disulfide, we would expect a nice peak from our exciton energy. And no matter which area that we tried, it was a little bit variable, as you would expect, because the distribution of rhenium atoms are not uniform, right? So that in specific, this is the best case area that we could find of any signature of having an exciton, and this is blown up by an order of magnitude, right? So that as we start to envision doping and playing around and kind of engineering our 2D materials, you always have to kind of be conscious of what are the ramifications, not only on the structure, as our X-ray diffraction measurements or electron diffraction would show you that we have our hexagonal structure. That you can get around a structural transformation at around 40 to 50% doping, as you would expect in our in simulations. But what we found is that the electronic properties really change dramatically much faster or much sooner with low levels of doping. We saw that we can actually get large atomic strains around atomic defects, and that we can actually now take these atomic coordinates and pipe them into electronic structure calculation methods to try to study materials this way. Not only can we do this with our electronic properties, but we can study thermal properties as well. So I'll just go over the next couple slides quickly, but we perform the same type of materials, I guess, analysis using moly disulfide and the tungsten diselenide hetero interface. And what you can kind of quickly see is if we look at this, especially the atomic level strains here, that at the surface, you are seeing some high level distortions or strains, kind of as you would expect. But one of the unique things that we were able to do is actually, in the same sense that we did in the previous study with the rhenium doping, is we can actually take the atomic structures and calculate our phonon dispersions. And one thing I'll just quickly kind of point you towards is we do see that closer to the interface, that we do see this kind of peak in phonon mode or energy. And we do see that that's correlated really well with our experiment, right? So not only are we able to see the atomic coordinates, but we're not only able to see how the atomic level strains take place, but we can actually start to understand from the microscopic level or from the ground up how that correlates to our electronic properties and our thermal properties as well. Just to kind of finish up, I think this is a really exciting time for material science in general. I think, a lot of times when I'm most interested in looking at disorder and trying to understand phase transformations and how the kinetics and imperfections are actually regulating these phase transformations. And really in the future, I hope that this kind of multimodal framework where we're taking our atomic electron tomography coordinates, we're trying to understand the microscopic properties and we're validating them with different microscopy and spectroscopy techniques can really hopefully, help solve some of the grand challenges in material science. And with that, I'd be happy to take any questions.
I was curious about the 2D material work and was wondering if you could speak on some of the differences if you studied them between single layer of the 2D material versus multi-layers and how that affects the strain. And also if there's any instrument limitations that would prevent you from being able to go to multi-layers without analysis.
Yeah, so that's actually something that we're pursuing right now, and that's something that we're interested in. Especially, I think when you start to think about the variation in interlayer spacing, I think it's quite interesting. Especially as you saw here in the monolayer sense, we see a lot of rippling. So that when you have two stacks, whether it's formed thermodynamically or naturally, or whether you engineer to have that interface, I think that's something that we haven't done yet, but we are actively pursuing. For experimental limitations, I think currently right now, we're probably limited to around 10 to 20 nanometers in our Z stack. So we can get at least a couple of layers in between. And it's a very good point. Thanks.
I have a quick question.
Mhm.
What was the most challenging part to work with the 2D materials? Or do you envision it that
Materials, you want an isolated particle. But then in this case, you can imagine a 2D film that when you're kind of rotating to higher degrees, you're seeing a lot of material. But we figure out a way to kind of project this and limit that difficulty in real space. And then from the experimental side, actually the atomic vibrations or the mechanical vibrations at higher angles did kind of pose a little bit of a problem, but we have deconvolution algorithms to kind of account for those effects.
Yeah, nice talk, and I have a few questions.
Mhm.
If you can go back to the very beginning at slide 4. It's quite far.
Maybe it's faster this way.
Well, this is where you talked about capacity. I don't remember the number correctly. Where you had the heat capacity graph and vibrational modes on the left. So in this one, yeah.
Okay.
Oh, this is 4. Okay, so you're showing me a different one.
Oh.
So you have many number 4s, I guess.
Right.
Yeah, what you show me here is a very smooth transition. So I have difficulty imagining that you can correlate this smooth transition to any changes that you are trying to correlate to your dispersion curves here. And can you say anything more about how this is done?
That's a very good point. So in this case, I'm just showing the entropy curve for single phase with temperature. So it's not actually going through any transition. I'm only seeing the deviation between different theoretical models. So what you would need to do in this case would be to get this curve for the diamond cubic phase and then also compare that to, let's say, your HCP or a different phase to kind of make that
So
comparison.
it's actually not a heat capacity.
No, it's an entropy.
I thought that you said heat capacity.
Yeah, I did say heat capacity. Very good point.
Okay,
Sorry,
so
this
I
is
didn't
the
hear
entropy
heat
curve.
capacity, but I was listening to you. So,
Okay.
so that's where the confusion comes from.
Mhm.
Okay. If you look at your doping experiments
Mhm.
of the disulfide or silver, I forgot which one you have.
So what is the doping level?
It's around 3%. So it's not, it's so
Somebody go.
Yeah. So one thing that's interesting, actually, it's if, because when these are all chemical vapor deposited doping, that you don't have a very uniform doping level, or it's difficult to control. So even where areas where we see one rhenium dopant that's isolated, we do see a very strong distortion. So in 2D materials, the doping concentration value, I think it's a little bit different because you're on such small length scales as compared to having like a block of silicon, I guess, but you're right.
Yeah.
That's a good point.
The other thing, and I don't remember the number of this, so I think it was 34, the one where you had vacancies in the column of, it was on the right hand side, kind of reddish color.
In the 2D,
Yeah, it was, no, it was in 3D, so that was the here,
okay.
that's one, yeah.
Mhm.
So you were somehow explaining that these arrows point to the vacancies, or I have hard time imagining how you actually see the vacancies in a hole.
Yeah, so I don't know if it's easy to tell, but this is bad. I should work on the color. Lack of intensity, yeah,
And therefore you conclude that there is a vacancy.
vacancy, correct.
Yeah, this is where, yeah, it's sounds like a reasonable conclusion, but I always tell my students, not seeing something is not the proof that it's not there.
Yeah, so one of the things that we do actually is validate our reconstructions so that we can take our reconstructions and then create two-dimensional images, and we can compare those to your dynamical scattering simulations, right? So originally, I think when you look at it's quite, or at least I personally believe nowadays, it's quite easy to see if you have vacancies because you have such a decrease in intensity in your TM micrograph, so that we can kind of at least pinpoint that or look at that in this column or in this tube.
So how many atoms are in this column? Do you know?
Oh, it's just two. It's a monolayer.
So this is a mono.
Yeah, it's a monolayer. So that when we see a defect in a monolayer, it's much easier to see a defect in if you're thinking about hundreds of nanometers of material.
Yeah, this is then another stretch that I have. It's like it's a
very, very interesting work. Like, I had some questions related to synopsis. In your modeling in the glasses, how much of that is coming from surface precision as we transition out the
Sorry, I couldn't get the last part.
surface precision as you move from the bulk
Yeah,
into a different environment?
yeah,
There's a huge difference in energy, some chemical potential, right?
right.
So the atoms, as you approach that interface, they are not necessarily the same chemical potential environment.
Right.
So when I look at the order you're seeing at the surface, how much of that is being driven by that huge drop in differences in energy?
Oh, I think
Not
it's.
necessarily whatever what's we're trying to do.
Oh, no, I think it's totally driven by the change in your surface energy, right? So as you would imagine, that the energy for heterogeneous nucleation would be much lower than in homogeneous or within the bulk. And I think that's why, especially for the palladium nanoparticle, we only see crystallization on the surface, right? When you look at the physical vapor whoops. the shape of it is quite, it forms kind of these nano islands. Right, so as the atoms are coming down layer by layer, we do see that, you know, like you said, I think it's purely surface driven, or as you would state.
Okay, so then a follow-up to that is in your free energy equation,
Yeah,
how are you accounting for that surface tension?
that we haven't got there yet. This is purely observational, right? So we haven't looked at the free energy. Pardon?
In your simulation, I can currently argue that now that surface time, whatever simulation you're doing
Yeah,
is a lot of guesswork.
the simulations were just in periodic bulk simulations for that reason, for at least the metallic glass
So
work.
how do you correlate between the two then? If you're missing a time in the theory,
Yeah.
how do you connect them to the experiment?
Yeah, so I guess in this case, we're only looking at the atomic conformations or structure within the nanoparticle. So we haven't really looked at the correlation length or how far away from the surface you have to have. Actually say anything thermodynamically about them, and that's kind of more in the future, but for these simulations and for this work, it was just to show that we can kind of correlate the two. But that's a very good point, and that's,
Correlation multiplication.
yeah.
And I have a very big question about your calculation about the strain factor and structures.
Mhm.
So I'm just curious, like what kind of like a specific constraint you use for the calculation and how sensitive that. For example, you can just hold the units, the supercell like volume constant and relax the atoms, right? Or you can just relax everything, right? And how sensitive that like condition will affect your results.
Yeah,
Thanks, man.
it's quite sensitive, and that's why I would probably leave it as a qualitative comparison, right? Because when you're kind of breaking up, especially it's easy in simulations to have periodic unit cells, and you can have well-defined, and especially like you said, if you relax your structures that way, it's very simple. And when we're actually taking our experimental data, what we found was that although there are some slight variations in the spread of our bands, that the actual fact that you're having this metallization kind of with precision is because, you know, they aren't actually the TM micrograph has to be the TM has to be calibrated for the true lattice parameter. And so in these cases, we do check the pressures different sizes. So we'll scale our lattice parameter to make sure that we're not having artificial effects, as you mentioned.
Was the question answered?
Yeah, Martin.
Any other questions? Yeah. Well, thank you for coming. We have a small token of appreciation from the department for you.
Oh.
So it's good.
Thank you.
And yeah, let's make Dennis again for the great stuff.
Yeah.